Yeah, I'm Remzi Arpaci-Dusseau, and I'm a professor, and actually I'm also the department chair of the CS department at Wisconsin. It's certainly my great honor to be here and great privilege. I was at that first FAST in Monterey so many years ago as a new assistant professor. And if you had told me 20 years later that I would be giving this talk, of course I would have been thrilled and surprised and flattered then. And I probably would have thought you were wrong. So it really is an honor, and thank you so much for having me. So in this talk, I'm just going to do a couple things. And I hope you indulge me a little bit. I think I kind of divided the talk into two pieces. The first is, by the way, if people are wondering, like there's lights that just blare on you, and it's like makes it very strange to look out. So if I look like I don't want to look at anybody, it's just the lights. It's not the audience. So in any case, I'm going to talk the first part about how I got into storage systems and why did I choose this path of spending so much of my life studying storage and I/O. And that's a bit autobiographical, and I guess for that my apologies, but hopefully there's something interesting in there about, everybody's, I think, career path is interesting to hear about, so hopefully mine is as well. And then the second part, I'll talk a little bit about what I'll call technology-driven research, where I'll do a little bit more technical work, not too much, and where we'll talk about how technology changes and how we can use that to find problems to work on and hopefully advance the field. And along the way, I'll try to point to some lessons learned, as promised, I guess, in the abstract, and hopefully those will be useful to anybody that particularly I think of like young students or young faculty members as a kind of a target for that. And I don't know how we want to do questions. I guess we're going to do them at the end. Is that the right thing? But I mean, if people wanted to do differently, I'd be fine too. So whatever works for the audience. So I'll just start with the autobiographical piece. I was an undergrad at Michigan, and like virtually everyone in CS, I thought I was going to work in artificial intelligence. That was true back then, 1,000 years ago when I was an undergrad. It's true now. When we look at our graduate student application pool, even today, like it's 3/4 AI. That's been true forever. Everybody hears about AI when they're a young person, and they think, I probably want to do that. Because it sounds cool, right? Artificial intelligence. And I was a little bit lucky. I got to work in a robotics lab. And so firsthand, kind of started to do some research as a kind of a sophomore, junior. And immediately, I came into a reason of why I stopped working in AI. And I call it the story of two robots. So what had happened was in the summer, a friend of mine, we were working together, two undergrads, and we were working on this classic problem in robotics, which is called obstacle avoidance. So has anyone worked on obstacle avoidance in robotics in the room? Oh, OK, at least one person, so I can't make up everything. But in any case, what the basic idea is, you have a robot, you have some obstacles, you try to move the robot around them, not run into the obstacles. Makes sense. It's like the first autonomous vehicles, right? And we had a sonar array on the front of the robot. So we put like a trash can over here and like a big box over there. And we spent all summer programming this thing. You call some routine to get some sonar array results, and then you come up with some algorithm. And by the end of the summer, we had something that kind of worked, and our robot slowly walked through the maze, very gently arranged maze, so we knew that it would work. And I felt pretty good about it. Like, hey, this is progress. This is how you do research in robotics. Unfortunately, or maybe fortunately, on the last day of the summer, there was kind of a fair, like a research fair of everybody who's doing robotics in the lab. Excuse me. Sorry. I'll grab a drink here. And there was another group that set up a robot that was also doing obstacle avoidance. The difference was it also had a sonar array. And actually, that's a picture of it. That picture with one of those robots is the one I'm talking about. And then instead of putting a trash can and a big box like we had done, they put a little minefield of pencils. So these tiny little objects, right? And I'm like, how are they going to avoid those? Super hard to sense. And they put like 20 of them. And then they said, OK, is everybody ready? And they looked like they were getting a little nervous about it a little bit because of the demo. And I'm like, what are they worried about? And then they hit go, and the robot went at like 50 miles an hour through this pencil minefield. It's like whoosh, and of course they're worried because if something goes wrong, the robot might fly into someone and kill somebody, right? So it's like a pretty exciting demonstration. And I was just, my mouth was open. I could not believe that the robot had first detected all those pencils and then moved at that speed through the pencil minefield. And so, I was an undergrad, I was kind of shy, but I figured I need to ask that professor who's in charge of that work, like, how did they do that? Because it was so much better than what we had done. I was kind of embarrassed at that point. And so I went up to the professor and I said, why is yours so much better than ours? Like, it's just 1,000 times better. And he said, oh, that's really simple. I'm an expert in sonar, and I study signal processing. And we just have so much better data than you do. You're just calling some library to get sonar data. You don't know how that works. And you're just writing the CS algorithm that you do after that. Me, I work with the data directly. So I kind of realized at that point, it was very instructive for me. And I think it's maybe the first lesson that I drew in life in research, was when you're working on something, you have to kind of ask yourself, how can I be the best at this? And in that robotics world, it was clear it wasn't doing the CS part of it that was going to make you the best. It was like being really good with the data, this sonar array. And so asking yourself what skills are required, what know-how are required in order to be the best at something is really useful. And for me, it was that moment I knew I wasn't going to go into robotics. So that's my first little story. So I had a problem then. I had to figure out my next thing to do. What should I work on? It's no longer my dreams of AI and robotics smashed by a fantastic demo. So I thought, well, where else is something interesting? And I ended up kind of thinking maybe computer architecture. And the reason I went in that path was really just a chance visit to a bookstore. A different friend of mine and myself, remember when bookstores existed? Like, you would go to them, they had books. You would walk around. This was actually the original Borders bookshop in Ann Arbor. So it was a huge bookstore. It was like the size of a department store. And there was a computer architecture section, right? Computer section, computer architecture section. And we kind of chanced upon this textbook, Computer Architecture, A Quantitative Approach. Famous then, I didn't know then, but soon to become famous textbook. This is the first edition. And it was just like such an exciting book. We started reading it on our own, like outside of class. It was so engaging. It's kind of just, how many people have read this book here? Yeah, a number of you. And hopefully some of you at least agree. Like, it just kind of gets you excited about computer architecture and this kind of approach of using quantitative measurements to really understand architecture deeply. And so at that point I thought, well, the robotics thing didn't work out. Maybe computer architecture is the way to go. And I guess I always say never underestimate the power of textbooks. It can really influence people. I don't think we appreciate that enough as a field. So I went to grad school, and when I got to grad school, I started working. You get to grad school, you kind of ask your advisor, what are you working on? And they were working on a new project. It was called the Network of Workstations, kind of like an early, using clusters to build large-scale computer systems project. So this is in the early to mid-90s. And the competition back then were supercomputers. So this is before the data center existed as a thing, right? So there was these big machines, but they were called supercomputers, and there were these very custom machines, right? Like the Thinking Machine CM5, or the Intel Paragon, or the IBM SP2. All these really cool machines, but they're all very specialized, had their own special networks, processors, everything. And the argument behind the Now project was that commodity clusters, just a bunch of PCs with a fast network between them was going to replace all that, which it kind of did, actually. And so even though I wanted to go work in architecture, it was pretty clear that this project, all the interesting stuff to do was in system software, right? Distributed operating systems and scheduling, distributed file systems, the high-speed network layers, which was all software too. So I kind of stumbled into systems, is how grad school happened. That was just something that happened by chance. And the first few projects I worked on were really kind of performance analysis. Like, we looked at one of these massively parallel machines, the Cray T3D, very cool machine, had DEC alpha processors in it. It had 20 different ways to communicate between nodes. So we did a very careful analysis of all the different communication schemes. I then worked on some scheduling work. That's actually some of the first work I did with my wife, Andrea. And that was just how I started grad school. I'd worked on some stuff, but I needed to figure out my direction. Oh, and I guess I can point out here that you can see that then I was Arpaci and she was Dusseau. Later we got married, and I don't know if I've told this story before, but I'll tell it again. We, when we got married, we had to figure out what to do with our names. And so my wife told me, my soon-to-be wife told me that, my options were pretty simple. We could hyphenate our names. Okay. We could keep our own names, or we could not get married. So it's my choice. So I chose, I think wisely, to hyphenate. And if you've heard that before, my apologies. But she might deny that that's a true story, but I think it's a true story. So in any case, we were kind of looking for the next thing to do, and we took a database class. The great thing about graduate school is you take classes often in things that aren't necessarily your exact focus. And I always think that's really good advice for students. Like, take classes in other things, because that's your one chance to learn from some expert in some field that you're not going to talk to ever again. And we had to pick a final project. Like a lot of these graduate classes had final projects where you would go and work on something. And we were trying to come up with an idea, and someone recommended, hey, go read this sorting paper called AlphaSort. It's this fantastic paper. It's called AlphaSort, a cache-sensitive parallel external sort by Chris Nyberg and a bunch of folks, I think that at Microsoft. And it was just the coolest paper. I don't know how many of you have read that paper. It's a fantastic read. I recommend it. And there was so much to like in it. Like, for example, there was all these standard benchmarks that they were using to compete with each other, to break world records and say, hey, we're the fastest sort. And even more fascinating was, even in this world where they were doing an external sort, right? So that means the data starts on disk. You have to do I/O to read it into memory. Then you sort it, and then you write it out. And of course, you might have to do that in multiple passes if you have too much data to do it in one pass. But the fascinating thing, on the DEC alpha system that they had, if they weren't super careful about the cache hierarchy, the sort went really poorly. So they would do things like read in a big record with a key in it, and then instead of just sorting and moving those big records around, they would pull the keys out and keep a pointer to the record, and then sort the keys and keep the pointers, and then kind of reassemble everything. Some very cool microarchitectural kind of optimizations to work well with a cache hierarchy, even though they were doing an I/O benchmark, right? You'd think an I/O benchmark sorting. So fantastic. It kind of inspired us. And I think that was something I also learned in grad school. It's like always great to use papers as inspiration. Like, find papers you really like and try to see where they lead you, right? That's nothing better than to have a paper that you think, oh, I wish I could do a paper like that. And this was certainly one of those. So we went to the professor and said, here's our proposal. We're going to use our cluster, our network of workstations, to break this world record. And they were like, this is a terrible idea. The people who do that work are professionals. You'll never be able to compete with them. So it was a little deflating. And so we went and thought about it some more, and we're like, we literally have no other idea. So we're just going to do this thing anyway. So I always tell people, like, advice is great, but you don't have to always take advice. You should just do the thing. Eventually, you have to decide what to do. And we just decided to go ahead and do it. And I guess you can probably guess how this turned out. It turned out well. We built something called NowSort. Of course, the reason it went well was, well, it turns out Andrea, my wife and project partner, as you can see in many things, she had done her whole master's dissertation, or master's thesis rather, on parallel sorting without the disk part, right? So it was in-memory parallel sorting on like the thinking machine CM5. And so she already knew how to do all that stuff. All we had to do was add the I/O piece, right, to read some data from disk. And we studied that, and we kind of took an engineering approach. And pretty soon, we actually broke the world record, right? So this graph here on the right, it shows increasing number of processors, or actually machines in the system. Back then, machines only had one processor in them. And it shows how much we sorted in a minute, which was then a large amount of data. We could sort about 6 gigabytes in a minute. So it doesn't sound like a lot today, so I appreciate that. My apologies for that. The computers have gotten faster. But we got up to 6, and you can see the record at the time. It had been eclipsed. There was a same person, Chris Nyberg, who was on the AlphaSort paper, went and he did a slightly bigger sort on this machine from SGI. It had 12 processors. I remember this very distinctly. It had 12 processors. It was called an SMP, a symmetric multiprocessor. Now we just call it a multiprocessor, but back then that's what we called them. It had 12 processors and 96 disks attached. And so that was the record. 1.6 gigabytes was the record, how much you could do in a minute. And we were on 64 machines. We could get up to about 6 gigabytes. And so we won the world record. It was cool. We got to meet Jim Gray. He gave us a trophy. It was fantastic. And for me, I think, and you can see the name thing happened then. So I got a few things out of this. And it was really, I think, quite formative. This class project, in a class that I didn't even necessarily, well, like, why am I taking this class? It seemed kind of interesting, but databases wasn't my thing. Andrea actually dropped the class, but she was stuck doing the project with me. So she's like, I'm not doing any more homework. She was a more mature grad student. And I got a bunch of lessons out of it, though. One was that storage was important in general. Like, interesting applications do I/O, have a lot of data needs. We had come from a world where, which is hard to remember, there was kind of a backdrop of a lot of scientific computing, but less, which didn't have as much of an I/O demand, at least some of the ones that we were familiar with at that time. So this new kind of applications, these data-intensive applications were coming around, and they seemed important. So that was good. Second, they seemed complex, right? Like storage and I/O, there's a lot of stuff in them. A lot of storage systems seem like there's a lot to learn about them. And I think complexity is always attractive to researchers, right? You want to see something that is worth studying, worth getting into. I always tell students, like, if you look at, like, if you compare, like, two fantastic papers from Google, right? The Google file system paper and the MapReduce paper, right? One's about storage, one's about computation. If you kind of like weigh the papers, like the GFS paper has like 1,000 things in it that they have to do to keep your bytes safe. And the MapReduce paper, fantastic and not diminishing it in any way. It's just like you try again. If it didn't work out, it's much less mechanism in it. Storage has so much complexity, and I was kind of drawn to that. And then finally, it's kind of fun to optimize. So especially in the era of the hard drive, I/O was so slow that if you did something smart, it became faster. And it just was fun to play with and fun to figure out how to avoid some random I/Os or whether, like in the sorting work, we were comparing things like should we use mmap or reads or all these little details in order to make it run fast, and it was fun. So it was really formative and influenced, I think, the rest of my career, that one project. So I'll just kind of wrap up, like, how did my dissertation wrap up from that sorting work? You're always looking for like the next thing to do. I always tell this to students, and I think it disturbs them more than makes them feel comfortable. But I always say, I never know what the next thing to do is. It's hard to know the next thing to do. If it were easy, then it would not be our research world, right? We never really know what the next thing is. So how do you find the next thing? Who knows? But what I found interesting, I was reading an different computer architecture book, actually. Apparently, computer architecture books are worth reading if you want some kinds of inspiration. What I found was I just ran across this thing called the Amdahl-Case rule of thumb. And it said a balanced computer system needs 1 megabyte of main memory capacity and 1 megabit per second of I/O bandwidth per MIPS, per million instructions per second, of CPU performance. Now, I don't know if that's true or exactly where that came from, but it was some sense of like how a machine should be built, a single machine, for it to be sensible for most workloads. And so a pretty natural question for us with this new platform, this collection of machines, was how do you build a balanced cluster? Like, how do you make that all work so that it makes sense for a lot of different workloads? And so we started working on that. The graph on the right, it's a little bit hard to make sense of, but I'll share it. This is from a paper from 1,000 years ago. And what it shows is, what disk bandwidth on the y-axis do you get before you saturate the different resources on the x-axis? So what you'd want them for a balanced system to be is for those all to be kind of flat, because that means they kind of saturate at the same time. And you'd want them to be as high as possible, because that's just higher is kind of better. And you can see things like, the memory bus, for example, can move a lot of disk bandwidth. It's kind of over-provisioned from that standpoint, whereas you run out of I/O bus and CPU and so forth. So that was just my next project, and I'm just mentioning it for completeness here. I did think it's useful to that all really came from just reading a book kind of randomly. There was this rule of thumb in there. It sounded interesting. And then we kind of took it and did a paper on it. So I think it's always good to read widely. And I recommend that almost in every talk I give. It's read widely. Just like you take classes, different kinds of classes, read widely, because you never know where you'll get an idea. But it led to this, what I'll call my graduation dilemma. And this is kind of the end of this part of the talk, or more or less kind of the graduate school part of this talk. Sorry, I'm checking the time. And I had a discussion with my advisor, which was, he said, you should graduate. You did that paper, great, you're out of here. And I said, no. I guess I felt kind of bold. I mean, looking back on it, it's kind of a funny discussion. I'm like, no, I'm not graduating. I refuse to graduate. And Dave, if you know Dave Patterson, I was like very lucky to have him as my advisor. He's just a very nice guy. He's like, okay, sounds good. and very supportive. And my reasoning was really simple. I had done a bunch of analysis, we had built some stuff, but I wanted to be more and more in this world of systems, where building big software systems was the center to what you did. And I felt like, therefore, I should build a system before I graduate and go look for a job on the job market. And of course, it led to the kind of last question I had in grad school was, what's the next thing I should work on? What should I do so I can build some kind of system, and when I go out and look for work, that I can plausibly claim to be a systems person? And where that last piece of work came from was, again, just like a tiny observation made actually when we were doing the sorting work. So when we were doing the sorting work, at first it was all about like, well, how much did you sort? But what we kind of realized was the interesting piece was not just how much we sorted or how we did it, but rather when we did it. And when we did it was always in the middle of the night. We waited till everybody went home. There was nothing running on these 100 machines, eventually 100 machines. And then we would like get the perfect run and get the peak performance out of the system. And if we did it any other time of day, it was like 2 times slower, 5 times slower, you name it. It was a lot slower any other time of day. But at 4 a.m., we could get a perfect run. And of course, it's because no one else was using the machines. And the way we had constructed the sort, it's kind of obvious once you think of it, is when you're running on 100 machines and you've done the sort, like you kind of assume all the machines are perfectly the same, you run at the rate of the slowest machine. So if like the last byte you get off of a disk or whatever. And so there's an experiment we did on the right here, which shows the relative slowdown as you do different bad things to one node on a very large cluster. So just affecting one resource. So the best case is on the left, which is just normalized to 1. I don't really need to show it there. And then like if you had a bad disk layout, that's the second bar, you'd run on just one disk of 100, you'd run 50% slower. That's actually drawn from a real example. So what happened, we were trying to break the record in the middle of the night, and the sort was running 50% slower. We weren't going to break the record. And so first you figure out, OK, what's going on? You figure out, oh, it's this one machine. OK, what's going on in that machine? You log in. And then we found that that machine, on the outer tracks of the disk, someone had put a bunch of stolen music. So that was a thing in that time. In the early days of the web, people would steal music and stash it somewhere. So someone was stashing some stolen music on the outer tracks. We were getting on that one disk the inner track bandwidth, which was about 50% less. So the whole sort ran 50% slower. And then similarly, if you have disk contention, you run 3 times slower. If you have CPU contention, depending how heavy it is, you run, 20% slower or 4 times slower. If you have a lot of memory contention, you cause a little bit of swapping, you can run 5 times slower or worse. And so it felt like there was an idea there, like that the sorting performance was so brittle that we could probably do better if we were a little bit thoughtful about it. And so I always say to students, even today, or I try to, some student of ours is going to say, no, you don't say that. Well, I want to say it, and I'm saying it now. So always keep your eyes open. When you're doing one piece of research, there's always little things that come up, little things you notice. And if you notice those and take notes and think about them, it could unveil kind of a next line of work. So something to think about. So that led to some work on something we called River, which was how to basically make sorting and other data-intensive applications fast, even when one machine isn't so fast. In other words, how to make it kind of sorting run well during the day and night. And we wrote a paper on it. We wrote it for a workshop then called I/O pads because it was kind of like a precursor to fast. Before there was fast, there was I/O pads. And you can see one of the reasons they changed is because they just got a much better name. So fast is a way better name than I/O pads. I hope the I/O pads creator isn't in the room. And if I've offended you, my apologies. I now realize this as I speak. So my apologies, I/O pads creator. And what you can see on the right is kind of how we did these experiments. We became methodical about introducing what we'll call performance faults into a system. Like this is like a sort running on, or this is actually just doing a writing out to a bunch of disks. So you want to write as fast as you can to a set of disks, but one of the disks might be running 5 times more slowly. And you can see if you do it statically, of course, performance just drops off right away. You have to wait for that slow disk to finish. If you instead give more load to the faster disks and less to the slow disk, it's kind of obvious, right? Just like most things after you figure it out a little bit. And I always say this is a precursor to some of the large-scale data processing stuff that happened after that. So this is in the late 90s. Some years later, MapReduce happened and kind of took off. And it's hard not to look at that as a missed opportunity, as we were doing all that work but didn't quite do MapReduce, so it's a bit of a frustration. What I always tell students, if you can't do the work that's cited 12,000 times, you can at least do the work that they cite a little bit. So it's kind of like, feels like a mild success, but maybe also a missed opportunity. In any case, okay, so this last part of the biography, I would say, is we're kind of moving more and more into the world of storage. And we've now moved to Wisconsin, or young assistant professors. And if you're trying to figure out the next thing to work on, a pretty natural thing, which I never know how to give advice on this topic, is we completely want to get away from our dissertation work at some level. Who thinks, I kind of wrote, who thinks large-scale clusters doing big data processing is important anyway, right? Who would think that? This is around the year 2000. So maybe that wasn't quite the wisest decision. But we wanted to spend time and learn more about storage and I/O. And as I wrote before, as I said before, it was interesting and it's complex and important, but also there's this opportunity. There's this burgeoning, the storage industry was booming, companies like NetApp and EMC, all sorts of stuff going on. And it felt like there's a lot to learn there and a lot to potentially contribute to. But you need to be specific. You need to work on something that kind of connected to the storage industry. So I'd given a talk on this before, like how to find research problems, like kind of this measure then build approach. And the idea, which I'm not going to talk about today, but I'll just mention, is to use measurement of systems, like deep measurement of how systems work and operate, to not just learn and educate yourself, but also to find real problems that exist, instead of just making up a problem. Like a measurement is a good way to find a real problem. And so you can think of there's kind of a cycle that you do all the time when you build systems, which is you build it, something, and then you measure it, and you understand it, and then you build it better. Or you could start at the measure, and you say you measure something that exists, and then you understand it, then you figure out how to build something better, right? You can kind of start anywhere in there. And then once in a while, through that understanding, you get to like a learning opportunity where you have you're like, oh, that's interesting, and it maybe leads to a new idea. Research is a learning exercise in the end. You're just trying to learn something that people haven't learned before. So yeah, I think we always have had this infuse our work, always think about what can be measured and how to learn from it. And the first thing we really did then is try to attack a classic problem with this kind of measurement-based thinking. And a very classic kind of bread and butter systems problem relates to layering. We build systems in layers. That's just true since the first systems. And there's so many reasons we do that, right? I show a simple example here of a file system and a RAID and disks underneath them. You can think of those three layers. Of course, there's application, or maybe there's a database on top of that and an application on top of that, right? It gets more and more complicated. And why do we do that? Well, it makes systems simpler, right? You can reason about one piece at a time, reduces complexity. Different groups can build those things, and they plug together and hopefully kind of work. But we also know, just very deep down, that it's inherently problematic. Excuse me. That you lose information. So for example, file system doesn't know where the blocks of the RAID is putting blocks across the disk exactly. You lose control. Like you can't tell the RAID can't tell the file system what to do exactly. And so, the question kind of lingering behind that is, can we use measurement to help? And an idea came. I remember very specifically when this idea came. It's kind of, we had been talking about this and thinking about things, and then one day Andrea called me, and she just kind of said the phrase gray box systems. I remember this because I feel like the way I remember it is she said the phrase, and I knew exactly what she meant. I think we work well together. We don't have to exchange a lot of words in order to understand each other. And I kind of like hung up the phone, and we just started working on it until, and I remember it as we just worked until we had a paper. And the idea behind this work was to use measurement in the system itself to essentially unveil properties of how the system's working so you can use the system maybe below you better. So our first example of that, it's kind of a funny, simple example, but it was kind of how we started thinking about it, which was like sometimes you were using an OS, it has a file cache in it, and you'd like to know what's in the file cache. If you know what's in the file cache, let's say you have one file's in there, one file isn't, you might want to access the one that's in the file cache first, because then it's going to go really quickly, and then you won't kick it out by asking for the other one first. And of course, it'd be nice if there was an interface to tell you that information. But what we figured is, with this kind of gray box approach, you can just use measurement to kind of guess. You can maybe probe a few pages and time how long it takes. And you say, oh, if these ones are quick and these ones are slow, I know these are likely in the cache. Maybe the whole file's in the cache. I'll access that one first. So kind of probe and deduce and benefit. And this graph, I'm not going to describe. I decided it's too much work to describe that graph. It shows that it's better if you do that. Literally all the graphs in this talk, it shows it's better if you do that thing that I just said. So we can go back and review it later if it's interesting to people. So that was kind of our first step. And then we but we felt like it wasn't the perfect thing. Like it was like a good first idea maybe. And we kept refining the idea. And we had been kind of looking downward, right? Like looking down application to file system to disks. Can we learn more about the layers below us? But one day, and I remember this, we had a meeting, and somehow we had the idea, just through discussion, right? Sometimes it happens, I remember the excitement of the meeting still, was we said, well, what if you kind of looked upward? What if the disk could figure out something about the file system? And soon we called this idea semantically smart disk. Now, that's a bad acronym, it turns out. It turned out SSDs would be popular, but not these SSDs. So that was a bad name. But hopefully, we thought it was a really interesting idea. And I think from the gray box approach, it was like that gray box idea felt pretty good, but it didn't feel like we had been looking at it quite in the right, most impactful way. So keep thinking about it, and maybe you get to a better idea. And I think that's what we got to here. So a lot of different examples of this work, and we wrote many papers about this topic. We improved storage system availability with this RAID system, which understood where, which files were which part of which block, so it could do better fault boundaries in the system. We did a fun paper called Life or Death at Block Level, which sounds very dramatic, but it's just about whether, before there was interfaces to tell you, could a disk figure out whether a block was live or dead, and then implement certain functionality based on that. And a bunch of others, right? Like how to do smarter caching, how to understand what the database structures are. And even one of these few papers that was published at FAST 05 that had some proofs in it. That's one of the very few papers I've ever done that had some proofs in it. And I think that by finding this kind of better problem space, we found a much more impactful route for the gray box idea. Across the body of work, something like, 750 citations. And many systems in the world do some form of this block introspection. And I know that because a bunch of people have come up to me and told me, hey, we do that thing that you wrote about, except it's usually in milder forms. We tend to go a little bit extreme in our papers. So that was part one. Deep breath. I'll see how I'm doing on time. I seem to be doing OK. How much time? When do I supposed to stop by? 10:15 or something? 10:15. OK, that's no problem. So that's kind of how I got into storage and how we started working in that space. Now we have to take a deep breath. This is the part of the class where I usually give everyone a break and tell them to walk around. But I don't think that's appropriate here. So we're just going to go forward into the second part of this talk, which I'll call technology-driven research. And this is about much more recent work. That was kind of the prehistory. And it's really trying to talk about something other than measurement-based research, right? So we've done so many papers like that where we measure something and understand it. I was looking through, we've written something like 10 plus papers just analyzing the reliability of different storage systems, whether it's NTFS or Linux file systems or RAID level RAID systems or virtual memory systems, just a ton of papers or error paths. So much, there's a lot of richness to be when you study things because you learn so much by doing analysis. But there are other methods that you can use, of course, to generate research, as you all know. And what I'll talk about today is something that's also pretty obvious, I think, which is what you can maybe call technology-driven research. That we are fortunate to live in a field where if you just by waiting around, a bunch of stuff changes, right? It used to be the speed of processors. That was the most amazing thing for many years, right? That it used to be that you would just wait a year and you'd buy a new computer and it felt way faster. That was amazing. That doesn't happen anymore. Now they just are exactly the same. So that's a sad thing. But technology does change. And especially in the world of storage, technology has been changing pretty rapidly. And so you can always ask a very basic question, which is, what's the impact on software systems because of this change? And so I'm just going to talk about a few pieces. Oh, I guess I'll give a little background before I get into that. In the world of storage, of course, there actually wasn't change to some extent. There was some kind of change, but not maybe as much as we think. Because from the beginning, it was about the hard drive. Right, from back to 1956, you can see how big they were. They were very large, 50 24-inch platters in this IBM system that stored 5 megabytes of data, and it cost you only $30,000 a month to use. It's fantastic. Amazing that it worked. The next generation became the size of a washing machine, right? So already shrunk, that had 2 meg platters. Of course, we know that PC drives in the 80s became commonplace. Eventually, like Seagate was formed. Much cheaper and faster, but still, a rotating medium. But the bigger change, of course, really happened with, as you all know, with the introduction really of solid state. Now, some of these ideas were invented, in the 80s, but really didn't become commercialized until, and really popular and widespread till much later. And that was certainly a quantum leap in terms of performance, right? From milliseconds into the range of microseconds, tens or hundreds of microseconds. And though they haven't supplanted hard drives because they still cost too much, hard drives are going to be around for a long time to store most of the data. They obviously have some big role to play and have been playing a big role, as half the papers in this conference can attest to. And then even further, the disruptions are continuing, right? So if you look at things like cross-point technology or Optane, as it's called, it's expensive, but even has some interesting performance characteristics that you don't see in flash-based SSDs. So the remainder of this talk, I'm just going to touch on a few pieces of work that we did in this kind of technology-driven vein, which is, how does the fact that we have a new storage technology affect how we build this maybe classic software system? The first one I'll talk about just briefly is the impact of SSDs on a certain style of a database, which is called a log-structured merge tree. That's some work we did on something called Whiskey. The second piece, I'll talk a little bit about the impact of something like Intel Optane on caching, just how you do storage caching. And that's some work that we call Orthus. And then the last piece I'll just briefly touch on is the impact of this very newest storage technologies like Optane on the most basic thing when we think about storage systems, which is how you build a file system. And so I'll just talk about those, and then we'll wrap up. OK. So what is this Whiskey work about? Well, we can all know that I think key value stores are important. They're used in many applications, services. And they're often implemented as log-structured merge trees, not always. This is the technology that was invented in the database community in the 90s, and then adopted really pretty fully by Google. And so at some point in the mid-2000s, started to become more and more popular as like a lot of the systems within Google and then elsewhere use this kind of structure to store data. Why was that? Well, it's really optimized for write-intensive workloads. So when you're loading a bunch of data into an LSM, it really does well because it turns everything into sequential operations. So instead of like B-tree updates, which can be very random, it'll turn operations like updates into batch sequential operations. And as we all know, with hard drives, that's a really good thing to do. In fact, if you can get rid of some random IOs to do a lot of sequential IOs, you're going to be winning in a hard drive because the difference between random and sequential was like a factor of 100. But of course, the technology changed. And so a natural question that we asked was, do LSMs work well on SSDs like they work on hard drives? Well, like I said, the background here a little bit, that you buffer writes in memory. We'll talk about this in more detail in a second. Then you sort them and you write them out into a file. And over time, you get a bunch of these files on disk. That's what your LSM starts to build up some more data on the disk. And so what you do periodically is you kind of read through them and compact them and turn them into some sort of more condensed form of the data instead of having a bunch of the same key over and over again. It's called compaction. And like I said, it's already optimizing writes to disk. In a little more detail, I'm showing here on the left like how an insert works in something like LevelDB, one of these kind of early common LSMs, and on the right is a lookup. And what's happening on the left in a few steps is like first key value pair comes in, you log something about that, you slowly accumulate it in memory, eventually you decide, okay, that's done, I'm going to commit it to the disk. That's steps 3 and 4. And then eventually step 5 happens, like I mentioned, that's that compaction phase where you read a bunch of those first files you wrote and then get rid of redundant keys and write out a kind of a bigger one. And you slowly can form a tree like that. So that's how you do inserts, and that's why it's all sequential and works pretty well. On the right, you see how lookups work. You start by looking in memory, and then you kind of slowly can go down the tree. So you can look in the levels at the top, or you can kind of look in further levels until you find the key that you're looking for. The problem that we noticed through measurement was a problem that's common. Of course, you can look in any storage system for this problem. It's a problem of I/O amplification. Given that I have to do a read, how much other stuff do I have to read to get to the data that I want? Or given that I'm doing a write, how much other I/O do I have to do in order to do the write? And so we have this workload here where we have a 100 gigabyte database that we load. and that's the writing piece. And then we do 100,000 lookups on it. That's the reading piece. And we measured how much I/O amplification there was. And this is just using level dB on whatever technology you want. And you can see the I/O amplification was ridiculous. It was massive. Like it was 14 for writes in this workload and then over 300 for reads. The database was so huge that almost everything, you had to just read a ton of stuff to find the thing that you were looking for. And this kind of made sense when you were using a hard drive, actually, because you were just doing a lot of sequential I/O still for the most part. But it didn't make so much sense for SSDs. So we thought we could do better. And the idea that eventually we had is actually goes all the way back to that sorting paper that I was talking about, that AlphaSort paper. Remember in that, they were just sort really quickly. They separated the keys from the values, and then they sorted the keys. And so the same idea actually worked really well here. Instead of keeping keys and values together in the LSM, we could separate them, just write the values out once, and then store only the keys and a pointer to the values in the log-structured merge tree. And then when you're doing all the compaction, all the crazy stuff that happens in LSMs, you're doing it on very tiny things, the keys, and not the values. The values are just sitting there, left alone. So we wrote a paper about that at FAST a few years ago. This says state of the art, sorry. And I think the lesson from that was like, use a good idea again, right? You don't have to even generalize it. It's like there was a good idea, which is sometimes when you're moving values around with keys, you shouldn't do that. Leave the values where they are, keep a pointer to them, move the keys around. And the results were pretty fantastic. As we increased the size of the value, like to some maybe unreasonable sizes, but just as we have bigger and bigger values with our keys, the difference between whiskey and blue and level dB and red became sometimes like a factor of 100. It's like some crazy amount, some crazy difference in performance. Literally the only paper we have ever written, and I think we'll ever write, where in some cases we do 100 times better than the previous system. And that was for loading, for lookup, something similar. Just a massive difference when you have larger and larger values. Because in the standard approach in LSMs, if you have large values, you're just spending all your time moving values around. It's crazy. It doesn't make any sense. So I think whiskey is an example of this, this kind of technology-driven approach, right? It's trying to, it's kind of the way this Lanyu, the student that worked on it, he talked about decoupling sorting and garbage collection because it would allow us to do the sorting on the keys only and then the garbage collection and the compaction stuff elsewhere. And it was SSD conscious. There's a bunch of pieces I didn't talk about. We actually exploit the parallelism of SSDs that we wouldn't be able to do with the hard drives. And it had very significant performance gains, like across a range of workloads, sometimes 10x, sometimes 100x. And like I said, it was a good example of technology-driven research. It's also a great example of graduate student persistence. The main student behind this, Lanyu, kept pitching this idea to us. And honestly, we were like, this doesn't sound like a good idea. It was just like we were told with our work on sorting. We kept saying, I don't think so. This probably won't work. It probably doesn't make sense. And he just kept working on it anyway. And eventually, we're like, oh, this is a really good idea. Appreciate that you kept working on it, despite our negativity. So thanks, Lanyu. OK, so that's piece one. I have enough time, I think. I'll talk about a couple more pieces of this technology-driven approach. And the next piece is on how some of the modern storage technologies affect how we might think about caching in a storage hierarchy. On this work we call Orthus. And caching is one of those fantastic age-old topics also in storage systems, right? That it goes back to the earliest computer systems. We have like a disk, a memory, some hardware cache, maybe layers of hardware cache, a CPU. And we always just imagine it this way. That's how you think about it in the textbook. That hot data moves towards the CPU and you keep it there. Cold data, you move it away. It's very natural and just how we should think about it, right? It's a central assumption. Performance, as you get closer to the CPU, should be faster. As you go further away, it should be cheaper and bigger, more capacity. And that's pretty natural to think about it that way when you're thinking about hardware, right? When you're building hardware, like that's how can you build a fast cache? You build a small cache. And so, and then if you have a big cache, it's slow and far away. And this idea actually, is so embedded, it's hard to not think of it. It's hard to think, should we do it otherwise? But at some point, we started thinking with some of these new technologies, and we've been doing some measurements, actually, of new technologies, and found that maybe the caching wasn't getting the most out of using some of these new technologies and systems. So to understand that, we did a little modeling work. And the modeling works like this. It's very trivial, really. It says there's a performance device at the top, which has a bandwidth B sub p, let's say, bandwidth in B sub p, p for performance, and a capacity C sub p. And then below it, there's like a capacity device. That's how we often think of like maybe a 2-layer stack, which has a bandwidth B sub c and a capacity C sub c. And normally how we think about caching is that the bandwidth of the performance layer is way greater than the bandwidth of the capacity layer, and that the capacity of the capacity layer is way bigger than the capacity of the performance layer, right? So performance is at the top, capacity is at the bottom, and what we're trying to build is an ideal device assembled from these two devices. We want to get the performance of the high performance device and the capacity of the capacity device. That's kind of an ideal device. And that idea is so old, in fact, it goes back to 1946 at least, that John von Neumann, when writing the famous report about how computer systems should be built, right, he had talked to everybody about who was working on computers and assembled this famous report. And that's, of course, why we call it the von Neumann architecture, because he was really good at understanding things. A very smart guy, of course. And what he wrote was, I mean, it's amazing that someone wrote this in 1946. Ideally, one would desire an indefinitely large memory capacity such that any particular binary digit number, I guess he didn't know to say bit, you know, or whatever. He wasn't quite perfect, would be immediately available. It does not seem possible to achieve such a capacity. We are therefore forced to recognize the possibility of constructing a hierarchy of memories, each of which has greater capacity than the preceding, but which is less quickly accessible. Look, prophetic, right? That's cache hierarchy defined 1946. We've just kind of been working on it forever. Even von Neumann thought so. But what happened with some of these new technologies that we were starting to play with was that performance of the performance layer wasn't that different than the performance of the capacity layer. So let's say you put an new Optane device in on caching on top of an SSD. Well, it was faster in some cases, but not in other cases, and actually it changed based on the workload. So we started to build some models around this. And I'm not going to get into the details of the simple algebra we did, but what this graph shows is as you increase the hit rate, you know, what kind of bandwidth do you get out of the system? And what the different lines are showing, blue, green, and yellow, are different ratios of performance between the fast device and the quote-unquote capacity or slow device. So on the left, or the blue one, or the bottom line, is maybe a more typical way of thinking about it, like the difference between main memory and let's call it a hard drive. So maybe that's 100 times difference, just to make that up. And you can see that unless you have a very high hit rate, you get pretty bad performance, because a miss is so costly, right, if you have a very slow device. But you can see quite a different curve. When you have two fast devices, one kind of similarly with similar speed on top of the other, you know, the curve looks much different. Performance isn't that bad on the left, though you do pay a cost for caching, right? You have to still get things from when you miss and so forth. And of course, they all end up in the same place when you have a 100% hit rate. But the thing we wanted to compare this to was a different approach, which is not a caching-based approach, what we call splitting or offloading, you might call, or tiering even. And the idea there is not to arrange the two devices in a hierarchy, but rather to treat them as both places where you could write data to or read data from. And so we built a model of that too, like how would that work? And instead of a hit ratio, we have a split ratio. So how much do you send to one device? How many I/O requests do you send to the other? And just imagine we could do that completely flexibly for simplicity. And you can see for the different device ratios again, like the blue ratio with the incredible performance difference, of course you have to give almost all the data to the fast device for it to, all the requests to the fast device to get roughly the performance of the fast device plus the slow device. But you can see the major difference is in the yellow line, where the two devices have similar performance. You, of course, have to split the workload equally. You have to give half to each so you can get the bandwidth of both of them. And you can see, of course, there the bandwidth that's quite a bit higher because both of the devices are fast. And if you compare then the two splitting approach and the caching approach, you can see that if you have two fast devices, like caching doesn't make sense as a basic premise, because you're defining the performance of a cache system is going to be limited by the performance of what you treat as the cache device. If in a splitting approach, you can get the bandwidth of both. You're getting requests sent to both of them. So yeah, we learned that modeling is useful from that work. And so the solution we worked on, and by the way, I say we a lot in this, and Back in the graduate things, that meant I actually worked on it and Andre worked on it. That was that we. Now when I say we, I mean the graduate students worked on it and we got to help them write a paper about it. So just to be very clear about that. And what we started working on is this thing called non-hierarchical caching. So we wanted to use caching as a baseline and use caching when it's effective because it's kind of easy to build a cache. We know how to build caches. There's thousands of papers on caching. But then add in other little features that allow us to use the other devices when caching wasn't being good enough. So like read offloading, like sending some reads to the capacity device when you can. And that was a paper we presented quite recently. The lead student, actually, Khan, is right there. So I think I've already kind of described this, so I'll just kind of go through it quickly. In classic caching, requests go to the performance layer, and then there's very static things that happen below that. But with this non-hierarchical approach, we could kind of route around the performance layer, send some requests to the capacity layer, if so desired. And then we can also do things like not decide to promote something. Right? So we can do like a bunch of dynamic decision-making around the system. So what was the benefit of that? Well, the benefit was very simple. So here we're showing classic caching versus our approach, non-hierarchical caching with Orthus. And what we're changing along the x-axis is the offered load to the system. So a 1.0 load means kind of the cache level is fully saturated. And you can see what happens with classic caching. When it's underloaded, it gives pretty good performance. When it's fully loaded, and even overloaded, it doesn't get better. It's not able to take advantage of the capacity device, even though there's a lot of workload being presented to it. Whereas Orthus, what it does, as you present more and more load, it starts giving more and more requests to the layer below. So it starts offloading a bunch of work, and therefore utilizes more kind of the sum of the bandwidths of the two devices. A lot more detail in the paper. So that's Orthus. And now this is the kind of last piece I'll talk about, and then I'll stop. And thank you for your patience. The last piece is impact of these modern storage technologies on file system structure. Again, one of these kind of core questions. How do you build a file system? And of course, what's interesting about that is we've been building file systems also since the early days of hard drives. And so much of our thinking is in OS structure and file system structure is based on that. And the problem that, of course, has occurred, and many people have recognized, is that devices are fast, but kernels are less so, right? That in the hard drive era, the fact that you're trapping in and out of a kernel didn't matter so much. It was really slow to access the hard drive. But in the modern era, it does matter, right? That devices can sometimes take a few microseconds to access. If you're spending a lot of time trapping in and out of kernels, maybe that doesn't work so well. So we came up with this approach, and we came up with is really adopted from elsewhere, an approach which we started calling a semi-microkernel, where we pull, instead of having an application on top of an operating system on top of the disk, it's a classic approach, we pull the file system piece out and make it a user-level server. So that's why we call it a semi-microkernel. It's not the whole OS, just a piece of it is kind of in this microkernel-style architecture. It can be built in user space, and it can be really quickly accessed. This is really taken directly from the Google work on Snap, if you've seen that work, where they do this for the networking subsystem. So here the idea is like take that idea and see if it makes sense in storage. And so we called it a file system semi-microkernel. And there's really a ton of advantages to this approach, which I won't talk about too much. But a lot of it relates to like developer productivity. Developing kernel code is hard and slow, as anyone here who's done that knows. Developing user-level code, well, still you have to be careful with it, but you have all the tools that you have of user-level development. You can get really good performance because it's just doing like a cache transfer to talk to this thing. And it also simplifies a bunch of other things. So I'm not going to talk in any detail about this work because I'm at the end of the talk, but we have a recent paper on this topic. And we've essentially built this new file system semi-microkernel, which is a bit of a mouthful, from scratch. And again, I say we built it. Of course, I didn't build any of it. But it's fully functional. It does a bunch of cool things happen when you do user-level development. You can like find somebody's lock-free library and just use it to do really cool stuff. It's very hard to pull those things into a kernel, but you can do it in a user space server. It does a bunch of dynamic partition and scaling tricks. It's a bunch of code. That's because we have these great students that write a lot of code. And it offers really good base performance and really good scalability. So on a big multiprocessor, in some cases, it does way better than ext4 when running a lot of parallel database instances. So that's just that, and I can't really get into the details because I don't have any time. So that's a lesson summary. I'll just leave it there if you're interested. Those are all the things that I claimed were lessons. Let me just run through them really quickly. When working on something, ask, how can I be the best? I think that's always good to do. Never underestimate the power of textbooks, so keep reading them, I guess. Use papers you like as inspirations. Sometimes ignore advice, which may be ignore all these things that I'm saying. Maybe I should scratch that one out. Keep your eyes open when you're doing research. You never know what little thing will pop up that'll lead to some bigger thing. Read widely, take notes so you can remember what you read. Ideas can be really close to right. I say this all the time. So keep thinking and refining what your ideas are until you get to the best version of that idea. Always think about what can be measured and how to learn from it. That was a previous talk I gave. Ask how new technologies change how we build systems. And then from those 3 examples, use good ideas again, like that key value separation. Modeling, of course, can be useful. Sometimes we forget that as systems people that simple models are really useful, even back of the envelope. And explore ideas from other subfields. So that idea of the network system being implemented as like a semi-microkernel, why not do that for file systems? So that's my lesson summary. Of course, the last lesson is to thank people. I have the great good fortune of working with my wife over many, many years. It's hard for me to appreciate that enough, but it's really been my great advantage. We've worked with many great PhD students. The ones in bold have finished their PhD. The others, I hope, will finish. So keep working. And of course, many more people, postdocs, master's students, undergrads. Privilege of working with so many people over so many years. One of the best parts of being an academic, the fortune that I have, is to get to work with all these people at such a cool part of their life where they're trying to figure out what they want to do. So for them, I say a real heartfelt thank you. And I'd like to say thank you for having me. Thanks.